My name is Christoph Csallner. There's an initial question over there? No?
Why is your last name like that?
That is an interesting question. And we can go into this after the talk. Good question, though. So I'm going to talk about DSD Crasher. DSD stands for Dynamic Static Dynamic. And the talk is about reducing false positives in bug finding. So I know that a bunch of you have attended the talk last week by Bill Pugh on findbugs. So findbugs is a similar system. It also aims at automatically finding bugs. And our system, DSD Crasher, is similar to that in that it's completely automatic, and it also aims at finding bugs. But our system is also a little different from findbugs in that it has some ambitious goals on reducing the number of false positives. And to achieve those ambitious goals, we employ a sequence of pretty wild program analysis techniques. But first, for the background. So we're interested in testing. And testing is very widespread. Many people use up to 50% of their time for testing. Some companies even have one tester per developer. So what goes into testing? So first you have to figure out what your program is supposed to do. Right, you'll go and read some design doc. You go and talk to your fellow developers. You have probably some emails flowing around. There are some Java doc comments. So you go and read all those and try to understand what your software is supposed to do. And then the next thing is write test cases, manually probably, to check whether your software is really doing what it's supposed to do. And both of these are really hard and tedious in both cases. So for the second problem, there are some approaches to deal with it. For example, our check and crash tool, which is automatic test case generator. So it will take away the second part, the writing your test cases manually, and it will generate those test cases for you. But of course, what the test case generator cannot do is go and read your design doc and go and read your email and go into your head and find out what the software is supposed to do. So that's still like a very big problem in software testing. And we are trying to attack that problem with DSD Crasher. So I've talked to a bunch of you before and about using static analysis tools, using automatic bug finders, and one of the biggest reasons is false positives. One of the biggest reasons that they are not used very widespread. And this is also recognized in the research literature. So here I have one quote from the ESC Java developers. And ESC Java is one of the heavyweight, deep tools that try to find bugs in software. And the authors say that the tool has not reached the desired level of cost effectiveness. In particular, users complain about an annotation burden that is perceived to be heavy, and about excessive warnings about non-bugs, particularly on unannotated or partially annotated programs. And that's sort of the standard usage, right? You have some source code and you have not annotated it with some special constructs. You just want to run the tool out of the box. And then they say that there is excessive warnings about non-bugs, and I also call them false positives. Another study, a recent survey, Router and others have run ESC Java and also other automatic bug finding tools on 5 different projects with a total of 170,000 source statements. And ESC Java alone produced more than 9,000 warnings for potential null pointer exceptions. So clearly that's like too much. And the authors conclude that there are too many warnings to be easily useful by themselves. And now I'm going to give you the high-level overview of how we try to attack that problem. So there are different kinds of inputs you could put into some method you want to test. For example, you could have a method that expects an integer parameter, right? So according to the Java semantics, you could put in like the smallest integers up to 0, -1, 1, up to the biggest integer. It's all legal Java. But then there's also a subset. And this is like the little smaller box here I have. And that box represents the inputs that are allowed according to the specifications you have. So for example, there might be some Java doc that says you're only supposed to put positive integers into this function. And clearly, this box is the box where we want most of our test cases to be, because they should find bugs in the behavior that's allowed by the specification. Now, some people might also argue that it would also be interesting to find bugs outside this box, like robustness problems, when you feed unexpected input to the function. But for many people, that's a low priority when they fix problems. So we try to concentrate our efforts on that box of allowed problems. And the way we're going about it is we're going to start out with a set of existing test cases. So, and these are supposed to be passing test cases. So they draw from the input domain that's allowed by your specification, and then they have some behavior that is also allowed according to that specification. So we're going to try to and observe those, and I have them in this box here, the existing passing test cases. And then we are going to try to generalize that behavior we saw to the box of the allowed behavior. So we're trying to figure out what was the specification of the original program. And then, so that was the first step, the dynamic, the first D in the approach. And the second step is we run a static analysis tool to exhaustively search that space we just restricted. You know, to like what find bugs would do, or like what other, like lint or PyChecker or other tools would do. And we will get some results of those tools. And those results are here in the bug finding box. And then as a final step, the last dynamic step, the last D, is to convert those warnings to test cases so that we can confirm whether those warnings correspond to real bugs or not. Okay. And now for an example to make that process a little bit more clear. So assume that you have a method you want to test, m, and it expects an integer parameter, right? And you have a set of existing test cases, two here, so one calls it with 1 and the other one with 2. So we run those two test cases with the dynamic step, infer specification that, hey, we have seen 1, we have seen 2, so probably what the programmer wanted is a method that works on all positive integers. So that's our guess. And we infer that specification I is bigger than 0. And then we annotate your original program with that specification and feed the annotated source code into the static analysis system. And the static analysis system will do its analysis, and it might come up with that there might be some problem if you feed in input that is larger than 5. So that's the result of a static analysis tool. And we're getting those constraints and solving the constraints. And one example is that let's try out 6, because it satisfies that constraint. So we generate a test case that calls your method with 6. And we will execute the test case and see whether it crashed or not. And only if or exhibits that behavior that we predicted. And only if that behavior really occurs, then we're going to warn you. Okay, so note here that we have excluded two kinds of false positive warnings. The first kind is we didn't even search in the negative integers. So we excluded those cases where we think it's probably excluded by the specification. And also we have excluded another kind of false positive which arise in the static analysis, where it might warn about something that can never occur under any circumstances because the static analysis system did not get the Java semantics right. So we also exclude those cases. And now for the concrete tools we're using to achieve that. For the first dynamic step, we're using Daikon. That's a tool developed at MIT by Michael Ernst and his students. So Daikon runs your code, first instruments it, runs it, and generalizes behavior. And it can also annotate your code with pre and post conditions. So we're using this, and then we are feeding the annotated program into ESC Java. ESC Java is extended static checker. You can think of like as a very heavyweight compiler that does all sorts of static checks. Inside, it uses the simplify automated theorem prover. And the result of that static analysis tool, we compile to test cases. And for that, we use our a few constraint solvers. That's a third-party constraint solver, and also our test case generation techniques. And then we generate general test cases, and you can compile those, or the tool even can compile those and execute those. And then only the runtime exceptions that occurred are presented to the user. So now would be a good time for questions, like about the high-level idea. No questions? Nobody's following? Everybody's sleeping? Come on, somebody.
If you need a question, I'm just going to wait till I can ask it now.
Okay.
It's interesting to me that you infer some, I guess you said pre and post conditions.
Mm-hmm.
And you may be saying this later, but have you looked at adding those as just semi-permanent development assertions to be checked anytime the program runs in appropriate mode?
So you mean the Java assert statement?
The pre and post conditions, which a lot of them I assume would be executable conditions, and to simply add them so that it runs in a kind of diagnostic mode, that they just always be there for that.
So, oh, okay. So I'm going to repeat the part where I think I understood what, what the question was. So I think the question is, once we have those pre and post conditions, we could just leave them in the code so they can get checked at runtime every time the program is executed.
You might want to turn it off in production or something, so they can be executed routinely.
Yeah, that's a good idea. So I have not looked at this. I mean, there are might be a few problems in there that you only have looked at a few executions. And now you say, okay, I've seen behavior a few times, and I will enforce that every execution in the future will behave exactly as those few executions that I've seen before. That might be a little too hard because you might have seen only a very limited subset. That's one part to the answer. Another part to the answer is that the pre and post conditions are declarative. So out of the box, you cannot execute them. You need some sort of a compiler which compiles them to actual runtime checks. But that compiler exists as their JML compiler. So you could do it.
Anton. You said that like seeing the test cases that take 1 and 2 as inputs, you assume the precondition that the input cannot be negative. But it could be it's measuring low temperature, like the temperature inside your fridge, for example, in Celsius degrees. And so lower is more likely than larger. So how can you make that assumption about the spec?
Well, we just make that assumption. And as you pointed out, we might be wrong in many cases. But also we might be right in many cases. In our cases, I have a few examples and they proved useful. So it seems to work in practice. So the question was whether the generalizing of few behaviors to specifications, whether we are right or whether we also might be wrong some of the times. And we might be wrong some of the times.
In the cases you're wrong, is there a way for the user, when it gets the test case, and can you see this precondition and say, well, but the assumption you made was wrong. You should be between -10 and 10 is what I meant. Maybe it doesn't write them initially, but if you give it a guess, you might be willing to go and change the guess.
Yeah, that might be very interesting. If the developer would be willing to look at those pre and post conditions. Yeah, definitely. I mean, if you have such a developer, that's great. Okay, now, so this is kind of the outline of my talk here. I'm going to talk about the different components that we're using. So I'm first going to start out with EC Java. EC Java was originally developed at Compaq Labs. It's like a research tool and is now maintained in Dublin by Professor Kinnery. So basically, it's a compile time checker. And we're using the current version, the ESC Java 2, and the current version recognizes pre and post conditions expressed as JML annotations of your source code. So JML is a Java modeling language, which seems to be the de facto standard these days. And also it supports Java up to 1.4, which is also nice. And besides those specifications that might have been generated by some tool or written by some user, it also knows already out of the box the pre and post conditions of primitive Java operations. So for example, it knows what the precondition is of a division operation. Or if you do an array creation, if you have to use the Java expression that creates an array, then it knows which precondition has to hold in order that the Java operation does not throw a runtime exception. So then basically use all this knowledge to derive potential violations of those invariants where at runtime a runtime exception might occur. Okay, and so basically it does an intra-procedural analysis. So it looks at every method in isolation. And I'm going to explain a little bit how that works. So it takes a method body, and inside that method body, it replaces every call to some other method or to some Java language operation to first checking the precondition of that entity and then assuming the postcondition. So it can use the preconditions that some tool has generated for some other method, or it will every time use the precondition it knows about the Java operations. So and once it has replaced all those calls, it will compute the weakest precondition of the method body of terminating in any state. So just returning legally some value or void or whatever. And the other states are those states where it does not return legally, but throws some runtime exception on the way. And these are clearly the states we're interested in. So we only concentrate on those runtime exceptions, like, for example, a class cast exception, because most people would agree that throwing a class cast exception is not a good thing. Okay. So easy Java, like many static analysis systems, produce false warnings because they do not completely follow or model the language of the Java language, the semantics of the Java language. And I have an example here. So we have one method, get10, that always returns the value 10. And then we have some other method, math, that uses that method and divides by the result of the first method. So we, just looking at that code, we know that this method always divides by 0, but divides by 10 and never by 0, right? But since EC Java looks at every method in isolation and it does not have any pre and post condition of that other method, it just says, okay, for get10, anything can happen, so it might return 0, and there's a potential division by 0 exception. And it will warn the user, and the user will become annoyed because this is clearly a false positive. And I would call those kind of false positives the easier kind of false positives because we can attack those by compiler warning to test cases and then see whether it occurs in practice or not. And we're doing this with the last step, like here, where we get a warning by the static tool and then compile it to a test case. And if it doesn't turn out, then we just rank it very low or just do not show the user. But then there's also the other kind of false positive, where I would say it's a harder kind of false positive, where the tool just cannot access the semantics, the specification, of your program. So for example, here we have another method, and the method is called forPosInt. So it only will work for integer values that are positive, and the method name says it, and there might also be some Javadoc specification that says it, only put in positive integers. So everybody would know it, except an automatic tool like ours. So the tool will go in and analyze that source code with all the analysis, and will figure out, so if I put in a negative value here, then the code will crash and will warn the user. But besides those false positives, there's also another subtle problem. So the method above might be called somewhere in some other method, right? And in that other method caller here, there might be some serious bug down there. But since we're not aware of the specification for posInt, all the test cases we're generating to find that bug might crash in for posInt, and none of the test cases might actually reach the real bug down there. So the lack of knowledge also prevents us from finding real problems. Okay, and this, I would say that's a more serious kind of false positives. Those you're going to attack with that first dynamic step. Okay, so the first dynamic step, we are using Daikon. how Daikon works like that. So it instruments your code. Basically, at every method entry and every method exit, it will add some code that writes the values of variables to disk. So when in the execution, every time the execution enters a method, it will write all parameter values, all the values of your fields, and so forth to disk. And similarly at exit, and also at exit also rewrite the return value to disk. So you end up with a long trace of values. And then the Daikon tool goes through that trace, and it has internally a list of potential invariants. So for example, it has invariant templates for one value is equal than another value. Or one variable is always larger than some constant, or some invariant on some container structure holds, and so forth. So it will check all the combinations of those variables, whether they satisfy the invariants or not. And every time one of those data points violates an invariant, it drops that invariant. So then it's left with a smaller set of invariants. In the end, if some invariant held a few times but was never invalidated, it will just say, okay, I assume that this is a general invariant and will also hold in all future executions. And then it can export those invariants as preconditions and as postconditions. So the invariant that held at the entry of a method will be the precondition, and the invariant that held at the exit of the method will be the postcondition. And we are using Daikon in a configuration that many people use it, which is we only use the simple invariants. So most importantly, one integer variable is equal, larger, smaller than some integer constant, or equal, larger, or smaller than some other integer variable. Or that one reference variable is always null or never null. So just simple things. But we found these are more, we have a higher confidence that those are true invariants. So you just ignore the more complex ones, where container structures are involved, or floating point variables, and so on and so on. And one small side remark is that Daikon expresses those invariants in terms of some of its own methods it has. But since we're using a static analysis system that cannot execute those methods, we need to provide a few pre and post conditions to those methods. So for example, we wrote pre and post conditions to that method here. Okay. So now the question is, how would we use these pre and post conditions? And that also relates to your previous question. So we're only going to use the pre and post conditions as additional assumptions. So the idea is to just restrict the behavior additionally, right? So for example, here we have this method and a pre and a post condition. So when we analyze the body of the method, we will assume that the input has to satisfy the precondition. So we exclude some behavior. We exclude all the input that violates that precondition. And so the drawback of this obviously is that we might exclude behavior that leads to a real bug, but I think that's it's okay, because no tool will find all the bugs, and for us it's more important to limit the number of false positives as opposed to find the maximum number of bugs. And similar, if you call the method and ESC Java copies the post condition, so it replaces the call with the post condition, pre and post condition, then we're also only going to use it as an assumption. So that means, so we're not going to use it as a requirement, as was suggested before. So using as a requirement would mean that we enforce every time that a method is called that really the caller only passes values inside the method that satisfy the precondition, because that might lead to additional false positive warnings. So it's very likely that we only observed a few executions and missed several legal executions. So we do not want to warn the user about cases where the code executed and violated some previously derived precondition. First of all, that would introduce additional false positives. And second of all, the user has never seen those pre and post conditions before, right? Because our tool inferred them, and they're in a language that they probably have never seen before, and they're big, long, and ugly, so we're not going to deal with those complaints of the users. And then one interesting technical issue that came up while using the Dicon inferred invariants is behavioral subtyping. So what is behavioral subtyping? So you might have some class C, some class super, and some class C, and C extends super, and both define a method M. So that means that M overrides the super M. And if you provide pre and post conditions for M, for example, the super has P and Q, and then you also provide pre and post conditions to the sub method. What does that mean? That means that in the sub method you can only define additional behavior, right? Because the sub method always has to behave as the super method when used as a super method. So for example, you might have an animal class and a dog class, and then the dog always has to behave as an animal when you use it as an animal. So that means you can only specify additional behavior down there. That means that the real pre and post condition of the subtype, so the real precondition is that is the behavior of the superclass and the behavior of the sub, or like logically or the union of the subclass. And for the post condition is when the method behaves as a superclass, then it has also to follow the post condition of the superclass. And if it is called as a subtype, then it has to behave as a subtype. And P and R might overlap in this case. So, but what happens if you do dynamic invariant detection like Dicon does? So how Dicon works is that it observes some behavior, and then it will associate that behavior with the method body that was executed. So in this example here, assume that somebody calls super.m, and every time it calls super.m, or no, let's say that every time super.m gets executed, it returns the value 1. And every time c.m, the method body c.m gets executed, every time it returns 0. So it might be, you might think it's reasonable to annotate the super method with always returns 1 and the sub method that always returns 0, right? But it turns out with the rules I just showed you, and those rules are also enforced, first of all, they're enforced by JML and also enforced by other design methodologies like design by contract and those, that if you put it together, that the sub method, the post condition of the sub method is that it has to return 1 and it also has to return 0, which of course no method can do. So that is equivalent to false. And once you have this, such an inconsistency in a static analysis system, that it might throw off that system very easily, because from false you can infer everything, and then everything goes wild. So to make that really works, to make the system really work, we have to fix this, and we are working on this. But I'm not going to talk about that because that's another paper, and it's like quite involved. Okay, are there any questions so far? Otherwise, I'm going to talk about the evaluation.
Can you go back to the behavioral subtyping definition? So, is this the definition of behavioral subtyping that JML and DSD Java?
Yeah.
Dicon doesn't know anything about this when it's generating invariants.
It should know that definition, but right now I think it's just a bug in Dicon.
But actual Java developers don't follow behavioral subtyping.
I mean, they have to. I mean, for the specification, they have to. If they want to write legal JML specifications, they should know about it. And when designing methods, I guess they also should do it, right?
So that when you do P or R, you're widening the precondition, right?
Yeah.
All right, I'll ask you all.
Okay. So question was, and I got that question also previously at Georgia Tech, because that's like a very counterintuitive thing, that definition of behavioral subtyping. especially while coding, I violate that myself. I mean. Yeah, we should discuss it afterwards, I think. But that's an interesting point also from.
You can set something, you can accept something in the written method that doesn't satisfy the precondition of the superclass.
Yeah, you're allowed to give additional behavior to work on additional cases. Okay, so we're going to resolve those questions after the talk. So let me talk about our evaluation. So the goal of the tool is to find bugs, right? So some people use coverage metrics to evaluate the value of automatic test case generators. And I think that's a really bad idea. Because assume you have one tool and it generates test cases and it achieves a coverage of 80%, but it doesn't find any bugs. And then there's some other tool where the generated test cases achieve a coverage of maybe 2%, but it finds 10 great bugs. So which tool would you pick? So the tool should internally cover all the code, right? It should not, I mean, there's no point in exporting all those test cases that do this great coverage kind of thing. Okay, so, and we evaluated our tool on 2 third-party applications. The first is a JMS component of JBoss. And JBoss is an open source application server. We used the 4.0 release candidate 1 version. And that part consists of 5,000 non-committed source statements. And the second testee is Groovy 1.0 beta 1 version, where we excluded some low-level classes. And the resulting classes are 2,000 non-committed source statements. And the interesting part about Groovy, from our perspective, is that, first of all, it came with a big set of test cases. And those test cases were developed like for their purposes to achieve the quality of their code. So they're completely unaware of our ideas with the inferring specifications and so forth. So that's an interesting case where you can see the value with test cases that have been there before. So those test cases were not developed just for our experiments. And we compared our tool DSD Crasher to 2 other tools. The first one is our predecessor tool called Check and Crash. And Check and Crash is more or less a subset of DSD Crasher. So it does not have the first DICON step. It only has the static analysis step and then the dynamic step where we generate test cases. So here we would expect the DSD Crasher does better in excluding false positives, right? Because, I mean, that was the entire idea of the project, that we can access the specification. And I have an example why DSD Crasher does exclude false positive warnings. So in this case, we have something from JBoss JMS, where this particular method throws a negative array size exception. If you pass in a negative value of length, and length is one of the parameters, so it seems like it should be part of the specification that you should not put a negative value for length inside that method here, because you will get that negative array size exception. So we ran 3 test cases which use the method properly. And from those 3 test cases, DICON inferred that precondition here, and that's, I'm all using JML syntax. Anyway, so that the value of length has to be equal as the size of that array. And when we use this precondition inside DSD Crasher, then DSD Crasher will suppress that kind of false positive. So for the Groovy experiments, very interesting to compare the runtime. So the runtime of DSD Crasher is a lot bigger than the runtime of Check and Crash, which is not surprising because now we have the entire DICON step in there. But it's still like reasonable. It's only 3 times as big as the other runtime. And in total, we were able to suppress 7 false positive reports. The last report that we suppressed was not a false positive. But that's just a engineering shortcoming of our tool because it produced a little more complicated constraints, and right now we are not able to parse them, but that should be easy to fix. The other tool we compared against is Eclat. It's by Carlos Pacheco and Michael Ernst at MIT. That's basically the DICON people. and it uses DICON, and also generates test cases and uses JUnit and all that. But for the static step, it does not have such a heavyweight analyzer as we have. So they mainly use random test case generation. But I also have to say that Eclat has a much bigger scope than DSD Crasher. So I'm only going to compare DSD Crasher against that functionality they have here. But the addition to that functionality, I'm comparing against, they have more stuff, right? So it's not completely fair. But I'm comparing to that part they have there. And so here we would expect that DSD Crasher finds deeper bugs because it has a deeper static analysis. And also finds more bugs because it finds those deeper bugs. So here I have the JBoss JMS components and only the class cast exception reports. And DSD Crasher found 3 of those class cast exceptions in 2 minutes. And I tried several configurations of Eclat, and I was not able to reproduce those 3, although Eclat searches for class cast exceptions. And I think I have an example. So in this case, we have a method getBytes that expects parameter of type object. And you can imagine if you use a random test case generator, then you can really come up with many cases, many values for object, right? But this exception only occurs for very specific object, because the object has to be instance of this byte array with a capital B. And only in that case, it will go into that branch and crash because the programmer now casts against byte array with a lowercase b, and you get that exception. So DSD Crasher found that and Eclat did not. And for the groovy experiments, we have a similar behavior that Eclat in different combinations I tried was not able to find the same bugs that DSD Crasher found in similar time. And again, because it was not able to basically solve complex conditions and come up with very specific kind of inputs that cause a particular behavior. Okay, so I have a few pointers here. And you can download the tool from my webpage and also the predecessor tools. And right, for the conclusions. So I've presented a 3-step analysis technique consisting of first a dynamic step, where we execute your code with test cases to infer the correct, to infer the specification of the code. And then you, in the second step, use a static analysis to only search in this restricted space. And finally, we'll convert those warnings produced by static analysis into test cases to verify them, and only show you cases where crash really occurs. And with that, I come to questions. Oh, this summer I'm working with John Penix mostly and Yu Chen, and I'm working on automatic test case generation. And I'm looking for a Google project to try the technique out. So if you have any volunteers here, anybody that wants to get test cases generated automatically, then we can talk afterwards. Was that the kind of answer you wanted? Okay. Other question?
Have you looked at the tool called Qt from Mr. Illinois?
Pardon me? Qt?
Called Qt.
Oh, yeah. I looked at. So the question is, have I looked at the Qt tool from a student in Illinois? And yeah, it's a related tool, and it does an interesting combination of symbolic execution and concrete random testing, right? So basically, it uses some concrete execution to help symbolic execution in case it gets stuck because the constraints are getting too complex.
So, I mean, could you comment on any comparison where that would be better?
And it would be very interesting to incorporate this into our static analysis scheme. So basically, it uses a very nice trick to improve static analysis. And our static analysis tool does not do that, but it would be interesting to incorporate it. Joe?
So I can imagine that if DICON gave false positive variance, it would be a problem with this technique. I was wondering if you looked at, if you try to quantitatively assess just how much any false positive variance reported by DICON could hurt you if the test sample that you used to infer the invariance wasn't sufficient in some manner.
So the question is, what happens if DICON does not produce good invariance? I mean, that's a problem. I don't have any quantitative results on that. But since we restrict ourselves to only high confidence, simple invariants, we are confident that, especially the something is null or something is not null, that seemed to be quite helpful. But as always in DICON, the more test cases you have, the more tests you can run, the better will your invariance be. And you're not only restricted to test cases, by the way. You can, for example, monitor your tool in production. And then the user can tell you, okay, this was okay behavior. So you get a really big execution trace. And by doing that, you also get better invariance. Question? Oh, definitely. Question?
So is this being videotaped?
Yes.
And will it be available outside of the world?
Yes. I hope. Thanks.